Hello everyone, this is Mo Hasanovic from Indian River State College. Welcome to the lecture 3 of fiber optics video series. Today we are going to talk about the behavior of light in optical fiber. So we are going to explain a few important topics that are related to the behavior of light in optical fiber. We are going to talk about how optical fibers transmit light. We are going to identify the basic optical fiber material properties. We are going to describe the ray and mode theory of light propagation and how it applies to an optical fiber. We are also going to state the difference between multimode and single mode optical fibers. We will explain how optical fibers attenuate and distort light signals as they travel along the optical fiber. And finally, we are going to try to understand the processes of light attenuation and dispersion. Let us first briefly describe the anatomy of the optical fiber. The basic structure of optical fiber consists of three main parts. The core, that's shown here in light blue, the cladding, that's shown here in the red color, and finally the buffer, that's shown here in black color. The core is made out of very pure glass and it's used as a light guiding region. The core is surrounded by a layer of material that's called the cladding. The cladding that's again shown here in the red color is made out of glass or plastic with slightly different properties than the core, and the main purpose of the cladding is to contain the light within the core using the concept of refraction that is going to be explained on the next slide. There's basically a few important functions that the cladding performs. It is basically reducing the loss of light from the core into the surrounding air. It reduces scattering loss at the surface of the core. It protects the fiber from absorbing surface contaminants, and finally adds mechanical strength to the fiber. For extra protection, the cladding is surrounded by an additional layer that's called the coating or the buffer, that's shown here in black color. The coating or buffer is a layer of, usually it's made out of plastic or some material similar to plastic, and is elastic in nature, and it prevents abrasions. And also the buffer prevents optical fiber from scattering losses that are caused by something called microbands that we are going to talk sometime during this lecture as well. Let's spend a few minutes talking about the refraction of light. Refraction of light is a natural phenomenon related to light that's pretty much responsible for the propagation of light through an optical fiber. It turns out that when the light passes from one medium into another medium, it is going to change direction of propagation. That's basically shown on this slide. If you look at the bottom right corner, you'll notice that the light is passing from air into glass, and we see that light is passing from the point A in the direction of point B, and then at point B it is hitting the boundary between the air and glass, and it's going to change direction and it's going to propagate in the direction of the point C. There's a few things that are important to mention here. If the light propagates from optically less dense material into optically more dense material, in other words, if index of refraction of the first material is lower than the index of refraction of the second material, light is going to refract or bend toward the axis. That is the case that's shown on this slide. On the other side, if the light propagates from optically more dense material, in other words, the index of refraction of the material is higher in the first material than the index of refraction of the second material, in such a case, light is going to bend away from the axis. The next important concept that is going to be covered is the concept of the critical angle and the so-called total internal reflection. These two concepts are extremely important for the propagation of light through an optical fiber. Let us assume that the light ray or incident ray is traveling through the glass. When that light ray, for example the ray number 2 shown on this slide, hits the boundary between the glass and air, a part of the ray is going to be refracted or bent into the air, as shown again on this slide. The bending will in this case occur away from the axis, since the light moves from optically more dense material, in this case glass, to optically less dense material, which in this case is air. As the angle of incidence becomes larger, for example, if we are moving from light ray 2 to light ray 3 to light ray 4, so if the angle of incidence becomes larger, the angle of refraction is also going to get larger, and ultimately the angle of refraction is going to approach 90 degrees. That is the case of a light ray 3, where we see that the refracted light ray is basically traveling along the boundary between the two media, between the glass and the air. In such a case, we are saying that the total internal reflection occurred. Internal refraction means that the light does not refract, does not pass into the second medium, does not pass into the air in our case. The angle at which total internal reflection occurs, in this case angle that's on this slide shown as I subscript C, is so-called critical angle. In other words, the critical angle is the minimal angle of incidence at which a total internal reflection occurs. If we continue increasing the angle of incidence beyond the critical angle, the total internal reflection is going to continue to occur. It is just that in such a case, the light is completely going to be totally internally reflected, and it's going to basically stay inside of glass, such as in the case 4, where the light ray is reflected back into the glass at an angle of incidence that is larger than the critical angle. This phenomenon that is defined as total internal reflection can occur only if the light passes from a medium with higher refraction index into the medium with lower refraction index. This is very important to remember. So only if we are passing from optically more dense material into if the light is basically moving from an optically more dense material into optically less dense material, that is a condition that's possible condition at which total internal reflection may occur at certain angles of incidence. This slide further explains total internal reflection. If you focus on the picture on the top in the top right corner, you'll see the whole bunch of light rays that are shown here in either yellow color or red color. Those that are shown in yellow color are light rays for which total internal reflection does not occur. In other words, the light is going to bend into the second material, it's going to bend into the air. As opposed to the two light rays that are shown here in red, for which a total internal reflection occurred. The light ray shown in the red color on the left side is the light ray at which the total internal reflection occurred at an incident angle of incidence that's equal to the critical angle. It's shown here as angle theta subscript C. If we continue increasing the angle of incidence, we see that the light ray shown in the red color here on the right side is going to be totally internally reflected back into the glass. It's also important to touch upon the subject of so-called acceptance cone, or the subject of how the light is launched into the optical fiber. To achieve the launch of the light into the optical fiber, some form of light source is used, such as laser diode or some other type of laser. How effectively the light is launched into the fiber depends on the angles or directions from which we shoot the light into the fiber. We define a cone, so-called acceptance cone, that's shown here on the picture on this slide, that basically determines acceptable shooting direction that would result in an effective launch of the light energy into the fiber. The light ray incident on the fiber core must be within this so-called acceptance cone that's also defined by the angle theta subscript A, and that angle is called the acceptance angle. A very similar concept is also a concept of so-called numerical aperture. Numerical aperture is a measurement of the ability of an optical fiber to capture light. Numerical aperture is also used to define the acceptance cone in an optical fiber. The formula is given on this slide that would enable us to calculate both the acceptance cone and the numerical aperture. This formula is shown in the bottom left corner of this slide. The concept of propagation of light through an optical fiber is described through two distinct theories. According to the first theory, light is described as a simple ray. This theory is so-called the ray theory, and it's based on geometrical optics. The advantage of the ray theory approach is that you can get a clearer picture of the propagation of light along the fiber. The ray theory is used to approximate the light acceptance and the guiding properties of optical fibers. It turns out that certain phenomena that are related to the light propagation through an optical fiber cannot be explained by the ray theory or by the geometrical optics. We need a different theory, and that theory is so-called mode theory that's based on the behavior of light as an electromagnetic wave. Again, this theory is called the mode theory, and it's based on so-called physical optics. The mode theory would describe behavior of light within an optical fiber, such as properties of absorption, attenuation, and dispersion. This slide dives a little deeper into the whole concept of the ray theory. According to the ray theory, two types of rays can propagate along an optical fiber, so-called meridional rays and so-called skew rays. Meridional rays are rays that pass through the axis of the optical fiber and are used to illustrate the basic transmission properties of optical fibers. Meridional rays can be classified as bound and unbound rays. Bound rays are the rays that remain in the core and propagate along the axis of the fiber. On the other side, bound rays propagate to the fiber by a total internal reflection. And finally, unbound rays are refracted out of the fiber core. Let's also spend a few minutes talking about so-called skew rays. Skew rays are the rays that travel through an optical fiber without passing through its axis. As you can see in the picture on this slide, if you look at the cross-section of the optical fiber, you see the propagation of a skew ray, and you see that the skew ray that's shown here in blue never passes through the center of the optical core. So those light rays are so-called skew rays. These types of rays are often used in the calculation of the light acceptance of an optical fiber. Also, the addition of skew rays increases the amount of light capacity of a fiber, but there's also certain disadvantages of having skew rays in a core. And the most important disadvantage is that the addition of the skew rays is going to increase the amount of loss in the fiber. As we already mentioned, the mode theory, along with the ray theory, is used to describe the propagation of light along an optical fiber. The mode theory is used to describe the properties of light that the ray theory is unable to explain, such as absorption, dispersion, etc. What does the mode theory use to explain these specific properties of light propagation? The mode theory is based on so-called electromagnetic wave theory that uses wave behavior of light, specifically light as an electromagnetic wave, to describe these specific phenomena that we just mentioned. It turns out that the light that propagates through the optical fiber can be shown as a set of guided electromagnetic waves that are also called the modes of the fiber. The whole concept of modes in a fiber is a pretty complex concept. So we are not going to go greater in detail explaining about the modes in fiber. We are just going to mention a few important things that are important to understand, so that we can draw a difference between so-called single mode and multimode fibers. As we already mentioned on the previous slide, the mode theory is using electromagnetic wave behavior to describe the propagation of light along the fiber. A very complex set of mathematical equations called Maxwell's equation is used to describe these so-called electromagnetic waves or modes. It turns out that there are very different types of modes. There are modes that are called TE or TM modes, and each of these have very specific properties with different peaks and valleys. If you can focus on the bottom half of this slide, you can see a few different modes of light that are shown that are propagating along an optical fiber. We have so-called TE sub-zero mode that has just one peak, one maximum, and then we have TE1 mode that has two peaks, one positive and one negative, and then we have TE2 mode, etc. It also turns out that each of these specific modes is very specifically determined by their wavelengths. Modes that are bound at one wavelength may not exist at longer wavelengths. The wavelength at which a mode ceases to be bound is so-called cutoff wavelength for that particular mode. So for a given mode, a change in wavelength can prevent the mode from propagating along the fiber. The mode is no longer bound to the fiber. In other words, we are saying that the mode is said to be cut off. So in other words, by controlling the wavelength of the light that we are launching into the optical fiber, we can control the number of modes that are propagating along that optical fiber. All that being said, an optical fiber is always able to propagate at least one mode, and that mode is so-called the fundamental mode of the fiber. The fundamental mode can never be cut off. The wavelength that prevents the next higher mode from propagating is so-called cutoff wavelength of the fiber. An optical fiber that operates above the cutoff wavelength is called a single mode fiber. So a single mode fiber is going to be the fiber that is going to enable propagation of exclusively one single mode. An optical fiber that operates below the cutoff wavelength is so-called multimode fiber. Multimode fiber is a fiber that would support multiple modes that will be propagating through its core. And on this specific slide, on the bottom right corner, you can see a propagation of multiple modes along the fiber, specifically shown two modes here, lower order mode and higher order mode in this specific multi-mode fiber that's shown on this picture. Okay, let us now conclude. Based on the mode theory, as we have seen on the previous slide, optical fibers can be classified into two distinct categories. So-called single mode fibers that support the fundamental mode only, and so-called multi-mode fibers that would enable propagation of multiple modes through the structure of through their structure. It turns out that the structure of the fiber can permit or restrict modes for propagating in a fiber. The basic structural difference is the size of the core or the diameter of the core. Single mode fibers are manufactured with the same material as multi-mode fibers, but the difference, as I already said, is the size or a diameter of the core of that specific fiber. So let's give a little bit more details about single mode optical fibers. The core size of single mode fibers is small. The diameter is typically around 8 to 10 micrometers. A fiber core of this size allows only the fundamental or the lowest order mode to propagate around a wavelength of 1300 nanometers. Single mode fibers propagate only one mode because the core size approaches the operational wavelength. And this is achieved by using a laser as a light source. What are the specific properties of single-mode optical fibers is covered on this slide. Single-mode fibers have a lower signal loss and a higher information capacity than multi-mode fibers. That's a very distinct advantage of single-mode fibers relative to the multi-mode fibers. In other words, single-mode fibers are capable of transferring higher amounts of data due to low fiber dispersion and are also considered to be low-loss fibers, which would increase the system bandwidth and length. Of course, this comes at a certain cost. The manufacturing of the single-mode fibers is much more complex, taking into account that the size of the core, the diameter of the core is much smaller than the diameter of the core of multi-mode fibers. So that's the disadvantage. And then second disadvantage, important disadvantage of single-mode fibers is that you have to use a much more complex and much more expensive light sources to launch the light into such a small optical fiber core sizes. As opposed to the single-mode fibers, multi-mode optical fibers can propagate more than one mode. Specifically, multi-mode fibers can operate over 100 modes. The number of modes that propagate through the multi-mode fiber depends on the core size and the numerical aperture. In other words, it depends on the acceptance code or directions from which we are launching the light into the optical fiber. If we are increasing the size of the core, and also if we are increasing numerical aperture or acceptance cone, the number of modes that propagate along that multi-mode fiber is going to increase. Typical values of the fiber core size are 50 to 100 micrometers, and typical values for the numerical aperture are between 0.2 and 0.29. Let's talk a little bit about the advantages of multi-mode optical fibers. Obviously, larger core size and higher numerical aperture would result in several advantages. Light is obviously launched into the multi-mode fiber with more ease. We don't have to use the light sources that are more expensive. The higher numerical aperture and the larger core size make it also easier to establish fiber connections. During the fiber splicing, core-to-core alignment becomes less critical. And also multi-mode fibers permit the use of light-emitting diodes or LEDs that are significantly cheaper than other light sources. They are less complex and they can last longer. So all these are the advantages of multi-mode optical fibers, but there are also certain disadvantages. Loss in the multi-mode fibers is much more pronounced than in the case of a single-mode fibers. And usually multi-mode fibers are used for shorter distances as opposed to single-mode optical fibers that are able to transmit the information over the larger distances. So similar to the single-mode fibers, multi-mode fibers are also described by their core and cladding diameters. In this case, 62.5 micrometers is usually used as a core, and the cladding has a diameter of 125 micrometers. So you can compare these numbers, 62.5 micrometers as a core size in a multi-mode fiber to 8 to 10 micrometers core size of a single mode. The transition between the core and the cladding can be either sharp. In such a case, we are talking about so-called step index profile, or the transition can also be gradual, which is so-called graded index profile. The two types have different dispersion characteristics and therefore different effective propagation distance. Multi-mode fibers may be constructed with either graded or step index profile. So what we are talking about here are the properties of the core relative to the properties of the cladding. If the index of refraction of the core does not change as we're moving across the cross section of the core, and also the index of refraction of the cladding is not changing, then we are talking about the step index profile. If the index of refraction is gradually changing as we're moving from the center of the core towards its edge and further into the cladding, then we are talking about the gradual index profile. Now that we defined two important categories of optical fibers, namely single mode and multimode. Let's talk a little bit about two important properties of light, namely attenuation and dispersion, that greatly affect the performance of a light in an optical fiber. Attenuation and dispersion are very much associated with the loss of signal in optical fibers. Many optical fiber properties increase the signal loss and reduce the system bandwidth, and attenuation and dispersion that are shown here graphically on this slide are main culprits that cause this specific loss of signal in an optical fiber. How do we define attenuation in a fiber? Attenuation is a loss of optical power as the light travels along the fiber. Mathematically, attenuation is going to be defined as the ratio of the optical input power to the optical output power. So if you have an optical fiber, we would be measuring the power of the signal at its input and the power of the signal at its output. We would be comparing these two powers. We'll see that they are different. We'll see that the output power that's getting out of the fiber at its end is going to be less than the power of light or the signal that we launched into the optical fiber due to so-called attenuation. Attenuation in optical fiber is caused by a few distinct phenomena, and those are absorption, scattering, and bending losses. On this slide, there is also a plot shown that specified three distinct windows of wavelengths that are being used to transmit light along an optical fiber. There is a first window somewhere around 800 to 900 nanometers, and then the second window between 1200 and 1300 nanometers, and finally the third window between 1500 and 1600 nanometers. It turns out that these windows of wavelengths are the most appropriate from the perspective of signal loss to be used to transmit light along an optical fiber. In other words, if you're using the wavelengths in each of these windows, the light propagation through the optical fiber is going to result in the lowest signal loss. Let us now briefly cover each of these important phenomena of light that are causing attenuation in optical fiber. Let's first talk about the absorption. Absorption represents the major cause of signal loss in an optical fiber. Absorption is defined as the portion of attenuation resulting from the conversion of optical power into another energy form, usually the heat. Absorption in optical fibers is explained by three factors: imperfections in atomic structure of the fiber material, so-called intrinsic or basic fiber material properties, and finally so-called extrinsic or fiber material properties, mainly presence of impurities. Next important phenomenon related to light that causes attenuation is scattering. Scattering losses are caused by the interaction of light with density fluctuations within a fiber. Density changes are produced when optical fibers are manufactured, and during manufacturing, regions of higher and lower molecular density areas relative to the average density of the fiber are created. So when the light travels through the fiber, it's going to start interacting with these different density areas that are shown in the picture, and when the light hits these higher or lower density small impurities, it is going to be scattered in all directions, and that's going to cause the loss of a certain power of a signal that's being transmitted along the optical fiber. There are many different types of scattering, so this slide goes a little bit more in detail explaining those different types of scattering. In commercial fibers operating between 700 nanometers and 1600 nanometers, the main source of loss is so-called the Rayleigh scattering. Rayleigh scattering occurs when the size of the density fluctuation, or these defects that are present in the fiber, is less than 1/10 of the operating wavelength of light. It turns out that the loss caused by the Rayleigh scattering is proportional to the fourth power of the wavelength. As the wavelength increases, obviously the loss caused by the Rayleigh scattering is going to decrease. If, on the other side, the size of the defect is greater than the 1/10 of the wavelength of light, the scattering mechanism is so-called Maille scattering. Maille scattering caused by these large defects in the fiber core scatters light out of the fiber core. Another cause of attenuation in optical fibers are so-called bending losses. If we start bending the fiber, a certain amount of light is going to get out of the fiber core. Bending loss is classified according to the bend radius of curvature. We may have so-called microbands that are shown here on the right side, and so-called macrobands that are shown on the left side. Microbands are small microscopic bands of the fiber axis that occur mainly when a fiber is manufactured and cabled due to the small discontinuities and imperfections in the fiber, such as uneven coating applications, as well as to the external forces that damage the fiber coating. On the other side, macrobands, shown here on the left side, are the bands having a large radius of curvature relative to the fiber diameter. And these types of macrobands occur when fibers are bent too sharply during installation. So let's go a little bit more in detail and explain about the macrobands. Macroband losses are observed when a fiber band radius of curvature is large compared to the fiber diameter, as we explained on the previous slide. These bands become a great source of loss when the radius of curvature is less than several centimeters. Light propagating at the inner side of the band travels a shorter distance than that on the outer side of the core. To maintain the phase of the light wave, the mode phase velocity must increase in this case. And when the fiber band is less than some critical radius, the mode phase velocity must increase to a speed greater than the speed of light. However, this is impossible to exceed the speed of light. This condition therefore is going to cause some of the light within the fiber to be converted into the higher order modes. These higher order modes are then lost or radiated out of the fiber. Another important cause of attenuation of light as it propagates along an optical fiber is so-called dispersion. Dispersion is basically causing the change in the shape of the pulse and also spreading of the pulse. If you look at the picture shown on this slide, on the left side we have three very distinct square shaped pulses that are basically the pulses that are being launched into an optical fiber. As these three pulses are propagating along an optical fiber, due to this dispersion, these pulses are going to change the shape from being perfectly square into being round, and also their duration is going to increase, so they will start spreading over time and they will start merging into each other. So this is going to cause a loss of information and certain errors that would occur in a transfer of information. So this is a very distinctive problem that's related to the dispersion that's occurring in optical fibers. So dispersion represents the spreading of a pulse of light as it travels down the length of an optical fiber. And as already mentioned, dispersion limits the bandwidth or information carrying capacity of a fiber. In other words, the bit rate must be low enough to ensure that the pulses do not overlap after they have been spread due to the effects of the dispersion. And obviously, lower bit rate means that the pulses are farther apart, and that the greater dispersion can be tolerated. But on the other side, lower bit rate means lower speeds or a lower amount of information being transferred over a certain amount of time. We can describe a few different types of dispersion. There's so-called modal dispersion, material dispersion, waveguide dispersion, chromatic dispersion, and finally polarization mode dispersion. Let's talk a little bit more in detail about the modal dispersion. Modal dispersion occurs only in multimode fibers, and it is the result of light rays following different paths to the fiber core and consequently arriving at the fiber end at different times. In other words, as the modes propagate along the optical fiber, light energy distributed among the modes is delayed by different amounts. So the pulse spreads because each mode propagates along the fiber at different speeds. Since modes travel in different directions, some modes travel longer distances. If you look at the picture on this slide, there's two modes shown in a core of the optical fiber. There's a mode shown in a red color, and there's also a mode shown in blue color. Mode that's shown in the red color obviously travels shorter distance from the left side of the optical fiber to the right side of the optical fiber, as opposed to the blue mode that travels longer distance. So the fact that the blue mode travels longer distance means that the blue mode is going to arrive on the right side or the right end of the optical fiber at some later time compared to the red mode. So that's exactly why the duration of the pulse that's being transferred through these two modes is going to increase, as shown here on the left and on the right side. So we see that at the beginning, both the red mode and the blue mode are perfectly overlapping, as opposed to the right side, where we see a delay of the blue mode due to the fact that the blue mode travels along the longer distance relative to the red mode. Another type of dispersion is so-called material dispersion. Material dispersion occurs because different wavelengths, different colors travel at different velocities through a fiber. It's important to mention that the light that's being transmitted along the optical fiber is at a specific wavelength, but that's not going to be just that one specific wavelength, but rather a short interval around that specific wavelength. In other words, there is a whole range of wavelengths around the basic wavelength that's being used to propagate the light along the optical fiber. And each of these specific wavelengths in a certain range are going to have different velocities. In other words, the modes or the light at different wavelengths is going to be traveling and reaching the other end of the optical fiber at different times, causing so-called material dispersion. Another word for material dispersion is also chromatic dispersion. So some use chromatic dispersion to describe the material dispersion. So chromatic dispersion is the term given to the phenomenon by which different spectral components of light pulse travel at different speeds. So it's shown more graphically on this specific slide. So if you look at the picture on the bottom, you see that we are not transmitting exclusively one specific wavelength along the optical fiber, but rather a certain range of wavelengths around that nominal wavelength. And each of these different wavelengths is basically shown here in different colors. And we see that each of these different wavelengths will be propagating along the core of the optical fiber at different velocities, thus causing the time delays on the other side of the optical fiber and ultimately spread of the pulse. So let's put spectral width and chromatic dispersion into the perspective here. So we've seen that due to the fact that we are transmitting different wavelengths around the nominal wavelength in a certain range would result in chromatic dispersion or spreading of the pulse. So in other words, we are very interested in reducing the spectral width of the light that is being used to transmit information along the optical fiber. Less wavelengths being transmitted around the nominal wavelength would mean less dispersion. The spectral width or the range of wavelengths that are being transmitted along the optical fiber depends on the type of light source that's being used. So if you compare the two distinct patterns here on this specific slide, one for the light source that for the light that's coming out of an LED, and another one that's coming from a standard laser, we'll see that the spectral widths are very different. So what we are getting from an LED is a much wider range of wavelengths. So in other words, if we are using LED, we're gonna get a spectral width of about 30 to 50 nanometers, and such a wide spectrum of light that's being transmitted along the optical fiber will ultimately result in a much greater chromatic dispersion, as opposed to the standard laser, which spectral width is about 3 to 5 nanometers, which is shown here in yellow color. So the width of the standard laser, spectral width of a standard laser is much lower, and the fact that we are transmitting a smaller range of optical wavelengths would basically mean less dispersion being introduced during the transmission of the signal using this type of light or this type of light source. So we are ultimately interested in using a light source that is producing light whose spectral width is lower. In other words, the range of wavelengths around the nominal wavelength is much smaller. So from that perspective, using a standard laser is much better than using an LED, but of course the standard laser as a light source is much more expensive, so there is a certain price that needs to be paid to reduce the chromatic dispersion in an optical fiber. Okay, let's now summarize the effects of dispersion on the signals that are being transmitted along an optical fiber. So in this specific case shown on this slide, the dispersion is reduced to an acceptable level. So a certain change of shape of the pulses is happening as they are being transmitted along the optical fibers, but what we receive on the other side are three very distinct rounded shapes of the three pulses that the receiver can read without any kind of loss of information. If the dispersion is increased, that's going to have an effect on the shape of the pulses and also on their duration. So we see that here in the bottom case, the pulses are spread to the point where they start merging into each other, and that's going to ultimately cause the problems at the receiver side. A receiver will not be able to read these pulses. In other words, we are going to have a certain loss of information. So this slide in a very clear way shows the effect of this dispersion on the signals as they are being transmitted along an optical fiber. So how do we explain why the receiver cannot read information, or how is the information lost due to the dispersion? So on this slide, on the top chart, you see basically two pulses that correspond to two binary ones, and then in the middle is no pulse that corresponds to the binary 0. Now, if these two pulses start spreading, we have a case in the middle where we still see two distinct pulses that correspond to the binary 1, to the two binary ones, and also we still have a break between the pulses that corresponds to the binary 0. If the dispersion is further increased, resulting in more of a spread of these two pulses that correspond to binary ones, they'll start merging into each other. So we'll be losing this, in simple terms, this break between the two pulses that corresponds to the binary 0. So the receiver will not be able to interpret the fact that it has received 3 binary bits that correspond to 1, 0, 1. Everything's gonna to the receiver. Everything's gonna look as a one long pulse that corresponds to the binary 1. So as we are going from the case on the top to the case to the middle to the case on the bottom, we see that how the increased dispersion has an effect on the transmission or specifically on the loss of information. Instead of receiving binaries 1, 0, and 1, we're actually receiving just one binary 1. So obviously there is a loss of information here that's caused by the dispersion. Okay, let us quickly summarize this lecture. So what we talked about today is the behavior of light in optical fibers. We have described the concept of refraction, and specifically total internal reflection as the main cause for keeping the light inside the core of the optical fiber. We have also discussed the basic structure of the optical fiber. We described or defined the core and the cladding and the buffer. And then we also talked about a few important concepts that are related to how the light is being kept inside the optical fiber. We have talked about, again, total internal reflection and the critical angle. We also defined the acceptance cone and numerical aperture. All those are important terms that need to be specifically described or defined for a specific optical fiber to be able to transfer the information from one end to the other. We have also briefly discussed about two distinct theories that are being used to describe the properties of light in the optical fibers. We talked about so-called ray theory, and we also talked about the mode theory. Each of these two theories are used to define or describe specific phenomena that are related to the propagation of light along the optical fiber. We have also briefly described two distinct theories that are being used to describe the behavior of light in optical fibers, namely ray theory and the mode theory. As far as the mode theory is concerned, we've seen that light that propagates along the fiber can be represented as a set of distinct modes. And from that perspective, we categorize the optical fibers into two big categories: single mode fibers that support one single mode, and then multimode fibers that support multiple modes. We've also seen and stated differences between the single mode and the multimode fibers from the perspective of their advantages and disadvantages. And then we also dived into the concepts of attenuation and dispersion, two main causes of signal loss in the optical fiber. We have described attenuation and important causes that are associated with the attenuation, namely the scattering and absorption. We also talked a little bit about the bands. We classify them into macro bands and micro bands. And finally, the last part of the lecture was about the dispersion. So we defined what dispersion means, what causes the dispersion, and what are the immediate effects of dispersion on the propagation of the light through the optical fiber, and ultimately on the transmission of the information from its input to its output. I hope that you guys enjoyed this lecture. This lecture is extremely important to understand the behavior of light in optical fibers, and if you understood these important concepts, it's going to be much easier to understand other concepts that are related to the optical fibers in the lectures that follow. With this being said, I wish you a nice day, and I'll see you next time.